Hello everyone, my name is Jenny. I've been working with my mentor Avantika and Professor Luke Thiagarajan's lab with the Department of Electrical and Computer Engineering through the UC Leeds program on particle trapping using dielectrophoresis. So chemotherapy is a treatment for cancer. It's a well-known treatment. What chemotherapy does is it targets cells that reproduce quickly inside of the body. However, it can't differentiate between cells that the body needs to cancer cells that it needs to destroy, which is why there are so many side effects to the chemotherapy treatment. My professor is working on site-specific drug delivery, in which the treatment only targets specific locations inside the body where cancer cells are present. In order to do this, the drug has to be encapsulated when it enters the body and only released once it reaches that desired location. The problem right now is we don't know what it is that will trigger this opening of our capsule. So we have to do experimentation in the laboratory. These particles are extremely small, so they have to be viewed with a microscope, which gives us a limited field of vision. They're also moving in fluid. If we want to, for example, add a drop of liquid to change the pH of the environment to see what happens to our particle, it will move our particle out of our field of vision. If we can't see what's happening to the particle, we can't determine whether or not our method is actually working. So Avantika and I had the objective to basically simulate and kind of model a method that will cause this particle to stay trapped when it's under observation in the microscope, even when there's fluid flow past it. So the method and phenomena that we've been working on simulating is called dielectrophoresis. It's a phenomenon in which a force acts on a particle and pushes it towards regions of either high or low electric field. We're using negative dielectrophoresis, so the forces acting on the particle are towards regions of low electric field. If you look at the image on the left, we have electrodes on the bottom. We have the particle in our channel that is above it. When we have the electric field on, the electric field at this electrode is high, so this peak right there. As it moves away from the electric field drops. As it starts approaching the next electrode, the electric field increases back up to the second peak. What we want to do is have our particle trapped in this area of low electric field as it passes over the electrodes. Similarly, on the picture on the right here, it's just a different electrode geometry. What we want to do here would be to trap our particle in this region. So we're using a software called COMSOL Multiphysics. And the reason why is we have to model both fluid dynamics and electromagnetism into one model. And COMSOL allows us to combine these two different types of physics for one simulation. So the Navier-Stokes equations are the ones that govern fluid flow. They allow us to solve for both the velocity and the pressure distributions throughout our channel. Our stress distribution is actually dependent on both the pressure and the velocity. And so the pressure and velocity differ at each point throughout the geometry, and therefore our stress differs at each point as well. Because our stress differs, our force is also different at every single point along the geometry, and this force is simply due to fluid flow. What we want to do is implement our electrodes, which are governed by Maxwell's equations, and our electrodes will produce an electric field that produces a dielectrophoretic force. This force will counteract the force due to fluid flow, as well as gravity and buoyancy, so that our particle has a net force of 0. So this is some of our data for the electromagnetism part of our simulations. We have our electrodes here at the bottom. There's 2 sets of them. They have a positive and a negative voltage, which induces the electric field between electrodes. And our graph on this side, the data is representative of this instantaneous time slice that we took of our simulation. And notice that the peaks are at the electrodes where the electric field is the highest, and our valleys are the areas in between those electrodes where the electric field is the lowest. And with this, you would normally see an even distribution of the peaks of the electric field. However, there's kind of an uneven distribution here, and that's mainly probably simply due to the fact that our geometry isn't completely symmetrical. So moving on to fluid flow, this is our velocity distribution of our geometry. We have our inlet here, we have our outlet over here. The walls have a no-slip condition in which the velocity is equal to 0. And notice that at every single point throughout this geometry, the velocity is different from each other. We also have our pressure distribution, in which The pressure is 10 pascals at the inlet and 0 pascals at the outlet, and it is an even distribution throughout. And the velocity distribution paired with this pressure distribution will give us varying results for the stress and force distributions. We have also been working on particle motion and simulating that on COMSOL. As of now, we've only been able to do it in 2 dimensions, but when we switch over to 3 dimensions, there are some issues that haven't been really worked out yet, but we're in the process. And so similar conditions, the top and bottom walls have no slip conditions, velocity is 0. Fluid enters at the left and exits at the right. The stresses due to the velocity profile of our fluid flow causes our particle to move to the right. It is also accelerating. This is also a really good example as to why we need dielectrophoresis. If we're watching this under a microscope and you add fluid somewhere to the left that pushes the particle and all of a sudden it accelerates to the right, your microscope only has this, that set field of vision. If it's out, you can't see it. You have to adjust it every time. So if you look at the particle right here, it looks just kind of a solid particle. There's nothing really going on. But in actuality, the particle is a little more complicated. It looks something similar to this. We'll have the drug in the center, and we'll have a bilayer membrane that surrounds it. This bilayer membrane is created by lipids in aqueous solution. And so there's a hydrophobic and a hydrophilic end to each layer of this bilayer membrane. And because this particle is not completely made out of one material or one compound, it has a more complex permittivity and conductivity. And so the overall effective conductivity and permittivity of the entire particle is dependent on both the conductivity and permittivity of each section of the particle as well as the radii of each section. So that can be shown with this equation over there. And so we have to incorporate these properties into our simulations in order to get the most accurate results. We want to be able to conduct experiments in the lab and match them up with our simulations and hopefully get similar results. And so the way to do that is to do testing with microfluidic channels. So this is our setup. We have a syringe pump that automates how fast fluid is entering our channels, and 2 syringes. One syringe has our lipid solution, and the other syringe has our aqueous solution. And these fluids enter through Tygon tubing that's connected to our microfluidic channels. If we take a closer look with our channels, this is a basic schematic. We have a lipid solution that enters at one inlet, and we have aqueous solution that enters at another. When they meet, they form together to form our membranes, and they get pushed further into the channel where the measurements are taken by 2 electrodes on either side. Once those measurements have been taken, they get pushed further into the channel and broken. And with continuous fluid flow, this process will repeat over and over, and we can take multiple measurements during the process. So we were working on this, and then we kind of caught ourselves in a dilemma in which our lipid solution actually reacts with the PDMS material we use to make our channels, which caused a deformation in our material and actually collapsed our channel right there. And that completely cuts off fluid flow and prevents us from forming our membranes. And so as of now, we are still in the process of working on a new solution that when heated to a really high temperature will form almost glass layer between the solution that we're going to be using and the PDMS material. So our future work with the simulations involves taking that 2D particle motion simulation and turning it into a successful 3D simulation. And once we can successfully do that, we want to be able to incorporate the buoyancy into our simulations. In the one that you guys saw, it wasn't running long enough for you to actually see the particle moving up and down, but we don't want that to happen in our overall simulations. We also still need to find the stress and force distributions throughout the channel to know what the force is due to fluid flow before we can implement our electrodes, which will generate a dielectrophoretic force that will cause a net force of 0 on that particle. With our channels, what we want to do is we have this new solution that we're trying to test out, and we'll flow it through our channels. And as it's flowing through it, we'll cure it with UV light so that it'll actually cross-link with our surfaces and form that almost glass boundary. And once we've been able to solve that problem with the reactions, we'll be able to make our membranes in our channels and take our measurements to input for our simulations. A special thank you to my mentor, Montika, as well as Professor Theagarajan, who have been working tirelessly throughout the summer with me, especially Avantika. She's been working with me and then immediately going to study for her screening, which is coming up soon. So a special, special thank you for her. As well as Sam, who is one of the grad students in our lab, and he's been helping us out a lot with doing things in the clean room that we don't have access to, as well as Erica and Javier for your guys' effort and contributions and feedback throughout the summer with my presentations, as well as CNSI and UC Leeds and OFI for the opportunity, as well as the New Innovators Award for my professor that is funding this project. Any questions? Yes?
So what is the diameter? I never caught. What was the diameter of one of these microfluidic channels?
They're about 50 to 100 microns in depth.
Okay. So the Navier-Stokes equation, it makes some assumptions about the fluid, right? Like whether there's like you have particle flow or just like. So I was just wondering if the Navier-Stokes equation takes into account the fact that you have very small particles.
So COMSOL actually has an option where you can say that the channels are basically very small in depth. And our simulations on geometry, they're all also on the micro scale as well. So the Navier-Stokes equations have been working fine with our small geometries, and it has the option of specifically specifying that it's very small channels. Yeah.
So you're doing this all so you can test the drug delivery capsules, right?
Mm-hmm.
So why is there a particular reason you can't just like have a beaker really, really full of the little capsules? So even if they move around, there's at least one in view whenever you try to open them up, instead of having to hold one single one in place.
You mean like while we're watching under the microscope, there's just a ton of them in there? So
Yeah, just that like.
I guess you could maybe do that, but I mean, it's just easier to be able to have it completely stationary before you add anything. Then you add that drop, and even though there's fluid still passing through it, it'll still stay trapped. And then you can physically see if it'll either open up, if you can see a drug being released or not, right? So. I mean, I'm not dealing with that. I mean, that's a little further in the project, and I'm not really dealing with that part of it. So I wouldn't really be able to answer your question as to why we would only do 1 or if not 1,000 particles. Yeah.
So this is probably also a lot further down the line, but I saw that on your diagram of the capsules that you have, hydrophilic drugs on the inside and the hydrophobic drugs like in the hydrophobic area.
Mm-hmm.
And are you guys like thinking about if there would be any structural problems? Like, would you always have to have both the kinds there, or would it affect the structural integrity to not have a hydrophobic drug there?
So that image that I pulled is like an image that was generated. I found on Google that someone else made that that might be directly applicable to them. And for me, I was only using it to show that the fact that there's more than one layer to the particle. And I am not working, once again, on the chemistry side of things where you work on the aqueous solution. But Avantika wants to answer your question. So.
Yeah, answer this question. Guys, that picture might be a little misleading. We are going to have lipid bimembrane. So the layer that is encapsulating the drug is going to be a lipid bimembrane. So it is going to have a hydrophilic as well as a hydrophobic part. But the hydrophilic part is going to be in the aqueous solution, the hydrophobic is going to be away. And similarly, the other way around. So there are going to be 2 layers, not just one.
Okay.
Back to back.
It's like a vesicle instead of a
Yeah.
bicep.
Does your model, or do you plan on having your model account for multiple particles? Not in the trapping, but just in the fact that in your solution, you'll probably have multiple particles that you'll want to trap just one particle from that. Or you
As in
gonna be
like
looking-
during fluid flow, we're gonna
Yeah.
have multiple particles
Yeah.
and try to trap all of them kind of
No,
thing?
no, no, but just trap, I mean, you're trapping one at a time, right? But in your solution, you're gonna have more than just one particle.
Right.
Are you planning on modeling that, or is that something you even need to think about?
I mean, yeah, it'd be a good idea to have more than multiple particles in our simulation. And I mean, the thing is, so like we have multiple areas that particles could be trapped, right? So we have more than one like region of low electric field. So I think if we do, it'd be possible for us to trap some particles in one region of it, but other particles could be trapped later on as well if they continue flowing in our channels. Yes?
As far as your solution to the channels interacting with your lipid, what are you changing the surface of your channels to? Is it more hydrophobic or hydrophilic? And do you suspect that if you solve the problem with it interacting with your lipid, will it interact with your aqueous solution?
So I think it's not so much that it's interacting with the lipid, but it's interacting with the solution we dissolve the lipid in. So to be honest, I don't have a chemistry background at all, so I wouldn't be able to tell you what is actually changing or what kind of layer is actually formed that creates that boundary. But the idea is that this new solution that we're testing, when it forms a hard boundary, it's almost like glass. So it prevents kind of it's less likely to have a reaction to something that's almost like glass. So that would be the idea. We want to have that boundary between our materials so that it doesn't come in contact with it at all. But we haven't gotten that far yet, and I honestly wouldn't be able to tell you what it's made out of or things like that. So yeah.
Great, well, thank you.